Moving right along with equilibrium constants, last time we calculated them. We used the ice chart. I gave you some concentrations to start with. We looked at how things change to achieve equilibrium. In this case, we're going to look at which direction a reaction would proceed under certain circumstances to get to equilibrium. Remember, the big things with these reactions is that we write them a certain way and we say reactants and products, but really because it's an equilibrium, either direction is good. So what we're going to look at today is something called the reaction quotient, Q. Q uses concentrations at any point in time to figure out whether more products or more reactants need to be made to achieve equilibrium. So what you're going to do, you're going to get K, and there's your equation for K. It's always the same. It's always your concentration of products over your concentration of reactants. Fair. It's been. It's been since we learned it in the fall. But K specifies that this whole deal is at equilibrium. So if I just take a pile, a cup, a dump of each participant and throw it in a container, call it the system and let equilibrium happen, I can dump in whatever I want and describe that as Q, the reaction quotient. And I can use my value for Q. I calculate it the same way I do K. I can use my value for Q to say which direction the reaction will proceed. Do I need to make more products as it's written, or do I need to make more reactants as it's written to get to K? So if I put in the numbers I have and Q equals K, I'm golden. I'm done. It's at equilibrium. I guessed right. Or somebody gave me equilibrium numbers just to see if I knew what I was doing. Fair. Likely? No. More likely than not, if you just throw stuff together, you're going to get a Q value, the value at a given time that's not what you'd need for equilibrium. If Q is bigger than K, so there's my Q. If Q is bigger than K, then it's the numerator that's too big. Too much products. I'll make more reactants. The reaction will go right to left. If Q is too small, if it's smaller than K, I have too many reactants, too much in the denominator, so the reaction will proceed then left to right as written. That'll make the change happen that brings Q back to K. If Q is bigger than K and I have too much in the top, I change some to the bottom until it gets equal to K. If Q is smaller than K because I have too much in the bottom, I make the top. And therefore, I go back to the equilibrium condition. That's it. That's all there is to it. If Q is bigger than K, I make reactants. If Q is smaller than K, I make products. Because remember, I need to use up the reactants to make the products and vice versa. So it corrects in both directions, making more of one while using some of the other. And this will work as long as I have Q, I'm not taking stuff out of the system. Has to be the closed system. All the conditions for equilibrium still exist, but I can predict the direction the reaction will occur. Let's look at some examples. They're just in the packet because they're basic math type stuff. So I gave you a KP, and it works for KP also, for that lovely Haber process equation that I just keep using. I make my Gen Chem kids look at 2H2 plus O2 yields 2H2O for a month of stoichiometry. And now you're getting this because it's a gas phase reaction and it could just be a regular reaction too. So I just keep using it. I gave you 3 partial pressures, one of N2, one of H2, and one of NH3, and said, okay, I threw that stuff in a container. Let's see which way the reaction proceeds. I write QP with my pressures, which is the same expression as I'd use for KP. I just can't call it KP because I'm not at equilibrium. It's like I got to call those things on the cart, those things that look like Pop-Tarts, I have to call them toaster pastries because they're generic. I can't call this KP. It's close, and it's the same equation. Like those are the same as Pop-Tarts, but they're not. I can't call this KP because it's not at equilibrium. So I calculate QP. Oh, wait, the same as I would calculate KP. NH3 squared on top, N2 and H2 cubed on the bottom. And when I get that, I I get 0.38. So I go back and compare to Kp. That's bigger than Kp. That's a good bit bigger than Kp with its 10 to the negative 5. Q is greater than K. I have too much product then, and I need to shift right to left and make reactants to get to the equilibrium condition. Now check this out. For the second example there, where I have no N2, I'm pretty sure I'm going to be making that, but I'm just taking a guess. Just pretend it's not there. I'm betting if there's none to start, that's probably what I'm making. And just looking at that, I bet I'm making reactants in this one if I'm missing one. So when I throw those in, notice it's the same equation. I just left N2 out. I have NH3 squared on top and H2 cubed on the bottom for 1.87. Making reactants again. It is bigger than Kp, and like I predicted, since I had no N2, I was making N2. So we're good there. Same thing. Here we go. I'm making reactants again. They weren't really original. I found this example somewhere. Same thing. Subbing in, calculating Q, moving on. And I had a practice here with using Kc that I could have put someplace else, but it's the same idea. It's still an application of the equilibrium constant, and rather than giving you notes on this last practice, I just threw it in there. I know 2 of my 3 concentrations, and I want to solve for the other one, where it's not using Q to predict the direction of the reaction, it's using Kc to calculate an unknown concentration. Basically, you put in X and you solve for X. There you go. Happy solving. The Q compared to K is the big message here and important. So keep that in mind. If Q is bigger than K, you're making reactants. If Q is smaller than K, you're making products. And if Q is equal to K, you're already at equilibrium. Have a great day.